Hello and welcome to the day 3 of week 3 of this lecture series. So I hope you tried practicing finding out conjugate elements for different point groups. If you have not, please try some more. So today we'll start from there where we left the other day. So we are talking about how to write this classes for one particular point group. So we showed that for C3V we write E 2 C3 and 3 sigma V, because all the sigma V's they belong to same class, and all the proper rotational symmetry operations they belong to another class, and E, that is identity, forms a class by itself. So the reason we club them together, and the reason is that their properties, their characters are same. Like the character of C3 and C3 square, they are same. The character of sigma V prime or sigma V double prime and sigma V triple prime, they are all same for C3V point group. Okay, but the character for this C3 class and character for sigma V class, they may not be same. Now, when I say about character, that has a deep meaning. So we will come to that in the following 2 or 3 classes. So let's come back to the classification of the symmetry operations. So on your screen, you can see that there is the D4H point group, and the classes that are possible for this particular point group are written here. So you have 10 different classes. So you have class by identity, inverse, and sigma H. Okay, they form class by itself. We have already told that, and here you can see that. And then 2 different sigma V's, they form class. 2 sigma D's, they form a class. Then C2, there is a C2 which is along the Z axis. In case of D4H Z axis means it's the same axis through which your proper axis of symmetry C4 runs. So C2 forms a class by itself, and then the perpendicular C2s, they form a class by themselves, and there are improper axis of symmetries. So this S4 and S4 inverse, they form also class by they form a class. Okay, so you have to try a lot of point groups, and you find out the symmetry operations, and then you perform the similarity transformation on them, and you try to find out the classes. Okay, so suppose I give you this D4H or some other, say like D4D, then there are certain troubles in front of you. What are they? Like just like that, if I give you D4D, how will you know what point group, what are the symmetry operations that this point group has? Because if I give you the molecule, maybe you can try to look at and find out what are the symmetry operations, or you have to think about a molecule which may have a point group D4D. But this is a little bit problematic. So another easy option will be to just go and find out a book of group theory, and at the end of this book you will always find a set of tables which are known as character table, and this character table gives you all the symmetry operations, but they will give in terms of this classes, but that will give you a right hint. But otherwise, how will you find out about the symmetry operations that a point group has? So like we are going in a reverse direction now. Earlier we figured out all the symmetry operations for a particular molecule, and then figured out which point group this molecule belongs to. Now what we will do, that in general, if someone gives me a particular point group, can I find out what are the symmetry operations that point group will have, and that's what we will look at now. So how will we do that? We will do that using something called stereographic projection. Okay, let me be clear at this point that we will not go into the details of the stereographic projection or the derivation of the stereographic projections. We will tell you the basic things of the stereographic projection, and we will show you how to use the stereographic projection to find out the symmetry operations that are possible. And also we will try to show you that by using stereographic projection you can find out the products of symmetry operations. That is an added advantage of the stereographic projections. So what is the stereographic projection? So any molecule will be disposed in a space, okay. So it's a 3-dimensional space. So anything, if you take it like a 3-dimensional sphere, and you project everything onto this plane at the middle of the sphere, you can take it like a mapping plane, right. So the stereographic projection is a particular mapping that projects a sphere onto a plane. So what we do here, we define a working space, okay, or working area, and we perform this projections of any point and utilize the symmetry operations to generate several points that are also projections of any point in the 3-dimensional space. So we generate different points, and thereby we figure out what are the symmetry operations other than which are very clearly defined by the point group notation that are present. Okay, so let's get started so that it becomes a bit more clear. So okay, so there are some issue in this particular drawing here. So this circle actually is meant to be here. So what I'll do, I'll just draw a circle here. Okay, that will solve the problem. All right. So this circle, big circle here, shown by a dashed line, is our working space, and everything that we do here will be within this working space. And then what we do, we take any general point on that particular working area or working space, and then we perform the symmetry operations. Now, which symmetry operations that we will be performing? See, when we look at the symbol, that is the Swain-Pline's notation for any point group, certain symmetry operations which are in that particular point group are pretty obvious. Let's say, for example, if I take the case of say C2V, okay. So what do we know about that? C2, that means definitely there is a C2 axis, and V stands for a vertical plane of symmetry, that is there is a sigma V. So these two at least I know, and E is always implied. So I will start from this first one, that is C2, then after I operate all the possible operations that is generated around C2. So here it is only one C2, because C22 or C2 square is identity, and then we will move to the next symmetry operations that is obvious from that point group notation, that is sigma V here. So we will apply sigma V. So similarly, if we have say like D6H, what will we do? So D stands for like Cn. So D6 means a Cn, then there are perpendicular C2s, and H means there is a sigma H plane. So these three at least I know. Now I do not know whether other than this there are center of inversion, whether there are other sigma V's, there are other sigma D's, whether there are improper axes of symmetry. All those things we can actually find out by using the stereographic projections. So let's get started. Now before we actually use, before we start stereographic projection, we will first look at certain symbols that are used here. So any proper axis of rotation is defined by some solid symbols. So like done here. So this is for C2, C3, C4, C5, C6, and you can keep going. So triangle is for C3, a square is for C4, pentagon is for C5, and so on. So it's not very difficult to remember also. And this particular geometry having 2 points on the two sides is symbol of C2. For improper axis, what we use is the same symbol, but not solid ones, but the hollow. Now, any sigma plane is given by a solid line. So, let me clarify these things a little bit here. So, suppose this is my working area, and then I find out that there is a C2 which is a proper axis symmetry, which is here. Then what I do, we mark it here, so that it means that there is a C2. So, for any given object here will come to this point by a C2 operation. Okay. So, if there is a C3, then I mark it here. Now, if there are perpendicular C2s, that is very interesting thing, right. So, this region is for principal axis of rotation or even improper axis of rotation, that is given the center, while any perpendicular C2s are drawn at the periphery. Okay. Suppose there is a perpendicular C2 here. So, say suppose this is a C2 perpendicular C2 axis, then you draw that sign here. Okay. This means a perpendicular C2, or if I write C2 prime. Okay. So, all the axis, proper axis or improper axis, they are written here, and any perpendicular C2 are written on the periphery. Fine. Now, this, whenever I draw any line, particularly when it is dashed line, that means nothing. So, that has no physical significance here. Whenever we see a solid line, that means something. So, these dashed lines are just for a guidance, that is all. Now, suppose this line is my sigma plane, then I will specify this one by a solid line, okay, across this. So, this is a sigma plane. Now, if there is any sigma h, what will you do? So, sigma h means this whole plane, molecular plane, you can imagine, is a plane of symmetry. So, then this whole thing will become solid. I mean, you will make it solid to signify that is a sigma h, that is shown here. Okay. So, with this basic knowledge, we will start looking at the stereographic projection of certain particular point group. So, the easiest one will be to look at something like C2V. Okay. I know that by now you know what are the symmetry operations that C2V point group has, but it will be a good idea also to use this C2V so that you can verify immediately whether you can use stereographic projection to find out what are the symmetry operations that are possible. So, we start here. So, you look at the the figure here. So, you have the working space here as usual, and what you know from C2V point group, that you have a C2. Okay. So, from C2V, what I know, I have a C2 definitely, and then I have a sigma V. Sigma V, you know what is the definition of a sigma V. So, now we start with C2. So, we take a general point here and then perform C2. So, if you perform C2 and if you do a clockwise rotation, then this point will come all the way and go right here, and that is what is shown in this figure. Okay. So, from here, originally it was here, and now I have here. Okay. So, for some reason this writing pen is malfunctioning, but that is okay. So, that is what we generate by using a C2. Now, we know that we have a sigma V. So, next I will use a sigma V plane. So, where we will use a sigma V? So, let us try sigma V right here, okay, in this direction. Okay. Now, will it generate something new? And we can see that yes, this will have a replica here, and this guy will have a replica over here. So, the result of applying sigma V after applying this C2 is this. Okay. So, now you see I am marking here also that this point was 1 and this point was 2. Now, this 1 prime and 2 prime have been generated by reflecting the points 1 and 2 through this plane, okay, which is our sigma V. Now, you see that 1 prime can be formed through a reflection on a plane which is here, okay, of the point 2. So, 2 and 1 prime can be generated from each other if there is a plane here, right. So I don't need to so I get another actually sigma v here. So if I call it like a sigma v prime. So now from this next, what we should look at is that, okay, I have applied both the symmetry operations that I could find out from the Swain-Fly's notation itself, that is C2 and sigma v, and operate both of them and generate all the points that are possible. Okay, so that those are the actual number of points maximum that you can generate, and after generating those, you see if one of the points could be generated from another point through any other symmetry operations which you have not looked at already. Okay, and we could figure out that yes, there should exist a plane here which we are calling it sigma v prime, by which you can generate 1 prime starting from 2 or vice versa. Similarly, 1 to 2 prime or 2 prime to 1. Okay, so we have now figured out that, okay, there are C2, sigma v prime, and no matter what, identity. So these are the 4 symmetry operations that are possible for the point group C2v, and you already know that. So you can see how useful this stereographic projection can be in order to find out the symmetry operations for a given point group. All right. So this is on your screen is what I just said, that is this 1 prime and 2 prime could be generated from a reflection of the point 2 and 1 through a reflection plane here. Okay. So from this example also you find out that the presence of C2 axis and 1 sigma v plane will definitely give rise to other sigma v plane, here 1 sigma v plane. Okay. So this is, no matter what, this is true. If you have 1 C2 axis, 1 sigma v plane, there will be another sigma v plane. And similarly, presence of a Cn axis and a sigma v plane guarantee that there must be a total n sigma v planes. We have already learned that while forming the point group. Okay, we had gone through the various steps, right? If you remember, step 1, 2, 3, 4, 5. So in those steps we mentioned that, okay, if you have Cn, do you have n C2 primes, do you have n sigma v's, do you have n sigma d's? So we know that if you have a principal axis of symmetry, that is Cn, then if you have 1 sigma v, if you figure that out from the Swain-Fly's notation of the point group, then you rest assured that there will be such total n sigma v's. Okay. So that's why this Cn axis and sigma v plane, they are called the generating elements of CNV point group. Okay. So for example, if you have taken C3v, you should be able to do that very quickly, right? So let me help you out in doing that real quick. So what you have for C3v, you first find out the you form a working space. So you are trying to figure out C3v. Okay. So C3 is principal axis. So what I know from this is that I have a C3 axis and I have a sigma v plane, and already we have learned that for C3 there must be 3 sigma v planes. So I already know that. Now I will start from here. So for a C3, let's put the C3 symbol here. Okay. All right, this is a solid triangle symbolizing C3, and then let's take any general point here. Okay, this is my general point, and for my own understanding, I am writing this this dashed line. Okay, so this is just to help myself. Okay, this doesn't have any other meaning. All right. So C3 means 120 degree rotation. So let me, I have taken this generalized point. So this is a generalized point, any general point on this workspace, and then I will operate C3. Okay. So C3 will take this one from here to somewhere here. Okay. Now my job is to complete the operations that can be generated from a C3 element, right. So then other operation that can be generated is C3 square, that means C3 and another C3. So this element will reach somewhere here after C3 operation, correct, C3 square operation, sorry. Now I have sigma v's. So next I have to operate a sigma v. So what I will do, I will say first take this one as my sigma v, one of the sigma v. So then I will get one right here. Now this point here will have a point over here, right, if I reflect it, and then this guy will have a similar point here. So now I have generated all the points that I could using the information that I have from the Schoenflies notation here. Okay. So I have used the C3, performed all the operations C3, C3 square, and then I have applied one sigma v, and I see the effect here. Now, so I have got C3, C3 square, I have got one sigma v. Now let's see. So let's mark these points. So like, you know, so say this is my point 1, 2 and 3. Now this is say 3 prime, and this is 2 prime, and this is 1 prime. Now you just okay. So from here you can see that this this x3 and x2 prime, they could be generated from a reflection through this plane. Okay. So if you draw it properly, it will be much more clear. And then this x2 and x3 prime, they could be generated, that is x2 x3 prime could be generated from x2 through a reflection on this particular plane. So what we get? We got total 3 sigma v's. Fine. So you can try doing many other point groups, and you can you know, from the point group symbol you can find out all the symmetry operations that you can generate. Now we also showed that, you know, with the stereographic projection we can find out what is the result of combining two symmetry operations, that is, you know, successive, you know, successively if we operate two symmetry operations on any particular structure, what will happen can be figured out by stereographic projection. So that will tell me that what will be the resultant symmetry operation. Now while looking at the group multiplication table also, we have figured that out, like, you know, here on front of you have the, you know, group multiplication table for C2V point group, and there you can see that all the binary products are written here. Now stereographic projection also does the same thing. So using stereographic projection you can actually find the group multiplication table. Okay. So they are all interlinked, you can see that. So now we will try to verify that you know, what will be the effect of you know, doing this successive operations. Okay. So now suppose I try to find out what happens when we operate C2 and sigma v successively. Okay. So that means I have to get sigma v C2, which means first you operate C2 and then you operate sigma v. So first I operate C2, so this point it goes over here. Okay, so this particular place is the original point that I took. Now after I got this structure, then if I operate sigma v here, what we get is a reflection, and in that case sigma v is in this plane. Okay, so a reflection will take it back to the original point. Okay, so we get it here. Okay, now sorry, there was a mistake, let me correct that. So you have operator C2, it comes here, and you take a sigma v which is along this plane, and you generate a similar point over here that you can see here, and then if you would have taken a plane which is here perpendicular to the sigma v plane, I would call it sigma v prime, then reflection through that sigma v prime plane could take the original point to this point, which we have got after operating C2 and sigma v. So that means that sigma v C2 equals to sigma v prime. Now let us go back to the group multiplication table and see if that is correct. So if you operate C2 and then sigma v, then you get this product which is sigma v prime. So this works. Now similarly, if we try to figure out what happens if we operate sigma v prime and then sigma v, what is the resultant? Okay, so we start from the general point, and the sigma v is this plane. So if we have a reflection, then I will go somewhere here, right here, and then if I operate sigma v which is along this, then I will generate a point over here, and that is what we have generated here. Now if I would have taken C2, so here it is shown like from here I can go to this point by C2. Similarly, from here I could come to this point. Okay, so if I could operate C2 from this original point, I could reach over here, which is identical to this structure. So that means that sigma v prime is nothing but equal to C2, and if we just have a quick look at the group multiplication table, then we can see that sigma v prime gives me C2, and also from here you can see that it does not matter which way I come, that sigma v prime or sigma v prime sigma v, it gives me C2, which also means that I can find out about the commutativity. Okay, so you can verify all the other products that you can form. Okay, so you can take any other point group, and I will suggest you to go in steps, like you go from say C2V to C2H, then higher order like C3V, C3H, and then D4, D4H, D4V, D4D, and try to generate all the possible stereographic projections, and you start verifying the group multiplication tables that you can have. So what it will do, it will it will give you enough practice, so that if you have to answer a question that what are the symmetry elements are present for this particular point group, you will not take much time and you can do it immediately. But the most important thing is that in the following weeks, what we will do, we will start moving toward the actual applications of the group theory and the symmetry aspects, okay, into actual chemistry problem. So essentially, for so far we have been preparing the basis for this applications. Okay, so when you go for those parts, particularly like finding out the selection rules or forming a particular symmetry adaptive linear combinations, we will be using something called representation. So we have to actually prepare representations of this symmetry point groups and their symmetry their elements. So there you would need to know this symmetry operations and elements pretty much, okay. And in order to be able to do that real quick, so that you can go to the actual problems, you should practice doing these geographic projections for more number of point groups, okay. So I will leave you at that point today, and we will come back in the following class with something more, where we will look at the matrix representations of different symmetry operations. Till then, goodbye.